All right, another draft physics video. I guess this is a production of some sort. Anyway, talking to Zohar again. Probably some questions, bits that he might not understand or not have, don't fully understand or something like that. But we'll see where it goes. So, welcome and such.
Okay, so I mean, I'm still a bit behind, right? But there's a couple of, I guess, new questions that I have. So one of them would be that if there's three objects that are kind of in a row, basically what you would have is you're not just doing addition, right? Like if you're trying to get, I'll try to change the color.
Well, object is a kind of an open word. So, do you mean electrons, protons, or do you mean force bits?
I mean planets, or it could be electrons, protons.
Well, planets are dipoles. So, in the sense that they are mixed dipoles, so they have a neutral. They don't do any of the charge phenomenon. So the force the only force that affects them is the actual movement. So a piece of them inside of them has to move or capture momentum for them to have momentum. So you have to think of them as things that absorb some force in some circumstances.
Yeah, so the idea is like that according to the model.
Well,
So
let's.
if there is like three planets aligned, let's say like the way I drew them, um, you so planet number three would feel um, like a force of gravity from planet number one.
And two, anything in its line of sight. So I'm just saying you have to think of number three. Well, first think of a cold universe, all right? So dead cold, and these are all cold objects. And you can sort of understand it as a thermodynamic argument, is that what motion is the absorption of temperature. So the warmer they are, the more they're already moving, the more they've already absorbed energy. That is, pieces inside of them have momentum. And that's how they absorb energy from the field. So once they reach thermodynamic equilibrium, then as much goes in as much they're radiating. But to become hot, they have to actually trap that energy. The energy, it doesn't give back. So when you have a temperature, you have absorbed some energy. You now have thermodynamics at that new higher temperature. But the fact is, you absorbed energy to reach the higher temperature. So all motion has to be absorbed. You can't have any if you didn't absorb motion to get it. So any objects that have any density in the theory would be objects that can absorb motion, and as they absorb motion, they absorb force that doesn't get where it was going. So yes, the force is blocked by number one. It's also blocked by number two. It's also being blocked by number three. So number four is going to have even greater gravity. So the
Yeah, but
gravity just has to do with how much mass is between you and any direction. So if you drew number three instead of the way you did, let's just draw it this way and understand number three is looking at the universe in all these directions. And all it's asking as it looks in all these directions is what is getting to me? Is there anything in my way from this force out here? Right? The force is coming from all directions out here. And so as it looks at the world, it's saying what's in my way between me and the force of the universe. All right? So this incredible dense thick heat that's in the universe. What is between me and that heat? And if there's something on that line, right? So the line goes through here. Well, then I'm going to feel less pressure pushing me this way. And if there's something on this line, then I'm going to feel less pressure this way. And that means the pressure on this other side isn't going to get equalized. And that means the tendency is going to be for this object to absorb momentum in this direction towards the objects that absorb the force that would have hit it but can't.
yeah, I understand that, but I'm just saying that basically the number one would be absorbing a certain percentage of the force bits, right? And then number two would end up absorbing it'll have less of a pool to absorb force bits from, if that makes sense. Like there's less force bits now going
But
through number two.
but that would only happen when you have a preposterous amount of mass. So you have to understand that force is insanely dense. And so you'd have to say, so that would have to be like a neutron star, where you have a limit on the well. Like unlike Einstein's gravity well, that's infinite. I'm arguing there's only a certain amount of pressure in the universe. So if you stack up enough matter as a wall, you will block the force. But the key to it is that you can only block it in the sense that you're going to force an electron, say in number one, is going to move. When that electron moves, it's going to move all the other electrons inside of there. And the movement will be pushing number one towards two. Well, one and two also are creating energy between each other. And so some of the energy from one is going to leak into two. So you can't really block all the force because the force just represents momentum. And momentum is pressure. So as you make more, if you put more and more matter, you're just creating an absence of the pressure that would have existed, right, if you didn't absorb the force. So again, but I'm just saying, for all practical purposes, you're not going to run out of this pressure until you get to insanely high pressures, right? I mean, the absence of pressure, say inside the center of the sun, in terms of the amount of gravity reaching the center of the sun, is probably minuscule. But the amount of chemical pressure, that is motion of electrons and protons, is huge.
Yeah, but then this makes it so that you're not just adding the two forces of gravity anymore, because now the fact that there is two of them makes it so that one of them is like has a bit less of a percentage of force bits to block, which means it's actually providing a little bit weaker. Like it would be an extremely small amount, and I'm pretty sure that
no, I would argue
almost...
I would argue that's not correct, only because number two is going to feel the motion of number one moving towards it, which means it absorbed force that was going to hit number two first. And so number two is going to feel less pressure going towards number one, okay, as a fact, just because one absorbed pressure that would have hit number two, right?
I don't think I understand that.
Well, the gravity is independent. Each object is producing a field. And so the field that the first object produces affects number two. The two aren't working completely independent of each other. Number two knows number one is there.
Yeah, and that's why number two is actually not going to produce like
no,
the effect that number two would have by itself would be different now, because now it's in a different field, and because it's in a different field, it doesn't have as many force bits to absorb actually in the direction.
It's still going to equal out because number two is going to move towards number one.
I mean, I guess just to make sure you know what I mean, I'm just saying like
gravity works both ways. I'm just saying 2 and 3 are affecting 1 just as much as 1 and 2 are affecting 3.
Yeah, that's true. But the thing is that 1 and 2, like if you had the picture without 2 there, and you just had 1 there, right? There would be a certain force, and we could call it F1. And then having 2 there without 1 being there would be F2, right?
No, so, because 2 is absorbing energy that would have hit 1. When 2 moves towards 1, it's absorbing energy that would have hit 1 on the other side. Right? So it's changed the force difference. We're really looking for the force difference, right? We're looking for imbalances in the force. Not so the only force you can measure, the only F is going to stand for is the imbalance. You can't measure an imbalance. So if the two forces are equal, there's no force. Right? We could agree on that.
I think so, but let me just change it a bit. So like, let's just say you were trying to find the force that the Earth would have on a person, right? And so I was thinking like you would just do like an integration, right? You would just integrate a lot of little pieces here. Like I'll just draw a little square or a cube, and you would just integrate all these little pieces, right? And the thing is though that the pieces that are farther away from you would be able to have a stronger effect. Well, they would be weaker because they're farther away from you, but they're actually still going to have an advantage because they have more of a force field, right? And by the time you get to pieces that are like closer to you, so I'll draw a little square here. by the time you get to pieces that are a bit closer to you, there's like a weaker kind of force field, so you're not able to block as much, right?
No, I don't agree with your premise because the pieces themselves are in the field. The pieces themselves are actually moving towards each other and away from each other. So you have to look at each layer of the Earth. The Earth is a bunch of layers, and each layer is pulling on each other layer and is in each other layer. So when this one moves, it moves everything on this side of the Earth, okay? It's essentially being moved by it, not just me. The entire substance of this Earth is all being affected a little tiny bit by each one of those things. So the event is not in and of itself an individual event. You have to think of it as the whatever is absorbed is going to be converted into a kind of pressure, okay? And the idea is it absorbed energy going this way. That's what we know because it moved an object. So it moved an electron. The electron is now moving slower than the force is moving. The force doesn't get where it was going. And again, but the only time that matters is when you're increasing the thermal equilibrium. So it's always going to achieve equilibrium. And the only time you can add gravity or add pressure is when you change the equilibrium. That is when you add more absorbed force, more movement. So you just can't, you have to start with one dust particle and then another dust particle and another dust particle, another dust particle. They all affect each other. They all start coalescing, and they're for the rest of their lives in a relationship where they are being attracted to each other. And, in the sense of charge, they're being repelled, so that's where it gets more complex in the formation of atoms. But that pressure always exists in the form of movement. Whenever anything moves in the universe, it absorbed a force that was moving the speed of light, and now that force isn't going to get where it was going. And where it was going was usually to hit its neighbor first, not something 10 billion light years away. So its neighbor is now being affected by the absence of that force. And its neighbor will be the first thing to move. And when its neighbor moves, then that's going to absorb another force in another direction.
Okay, so I wrote like the little integral. I mean, it's not really anything too serious or anything, but
well, I mean, just reverse that integral, okay? Because we could maybe agree on this. If we inverted that circumstance and we made a crust of the Earth and we put the person on the inside, you would agree there's no gravity in there, right?
Yeah, so that I think is fine because you're in the middle.
Well, I'm just saying, you're saying there's a disproportion, that somehow the force gets disproportional, that there's more surface on the backside of the Earth. I'm arguing, no, it all equals out. You can't make it unequal. So there's no thing as the closer object absorbs more force. It doesn't, because the absorption of the force is being converted into movement by the atoms, which is the same thing as pressure. It's forcing atoms closer to each other, which is creating more pressure. So you can't run out of force in the sense that the force is being converted into chemical pressure. The atoms are moving closer to each other, are impacting each other more often, which is movement. So the fact that you've made more movement means that you're making more force. So the force, when it finally gets to my feet, is still going to be substantial from those distant objects. The distant objects are what's pushing me off the surface of the Earth.
Okay, I guess I'll try like one last time and then we'll move on to something else. But basically, so you could use this equation, right? Like gm1 over d squared or whatever. You could probably use that for all these pieces basically in this integral, right? And you could get all the pieces to you could basically get all the pieces to like.
I'm just disagreeing with the premise that equation is complete because it doesn't account for the fact that you've converted the force into motion of the electron in the same direction of the force, yet at a much slower speed. So you still have the momentum is still there. You haven't eliminated any force. You haven't gotten rid of the momentum. The momentum's still in the Earth. The force isn't absorbed in the sense of it's just consumed and it disappears. It's completely conservative. You can't have movement without movement causing the movement. So you're replacing one form of motion with another form of motion, but the amount of force it equals is exactly the same because the big giant electron has a huge mass compared to the force bits. Therefore, the huge giant electron moving represents a lot more force than a single force bit moving, so to speak. So that's why it's moving so much slower. So all you've done is change the speed of the force by making an inverse relationship between speed and mass. When the force is moving fast, it's going the speed of light. When the force is moving slow, it's in a heavy thing. So the mass goes up as the speed goes down. And that's what makes it all end up being equal.
Okay, I think that's good enough.
Okay.
So another question I would have is like I don't think that we need to use the word matter bits, because we could just say that. I think the real thing that I'm really wondering is how would matter get trapped, right? Like how is it, what's causing it to get trapped? And I feel like it would have something to do with
Well,
electrons
I'm
and
saying
protons.
I'm so comfortable with the term matter bit because that's what it is. Okay, so frankly, I got no problem with that. There's only two kinds of it: electron and proton. That's it. There is no other matter. There's electrons and protons. Name me some other piece of matter in the universe.
Yeah, I don't think there is any other. But I feel like maybe we can come up with like a mechanism for why they would, like maybe you could have like a reason for why.
It's like that's like doing abiogenesis. That's just guesswork. Okay, so I can just say the reason is there's a membrane. All right, so if I create a membrane out of dead photons, so let's say there's such a thing as a dead photon, and that makes a membrane, right?
Wait, are you
And
drawing
then,
somewhere?
well, I'm drawing on the same board.
Yeah, I see, I see.
I mean, I don't know whether these are yours. Mine didn't. I wasn't undoing anything. Nothing else is undoing. Can you undo anymore?
I think it's all you now. Like I'm pretty sure I can undo it. The rest.
It's not undoing. All right. Well, let me just.
Oh, no, it is. It's you're just undoing those little dots that you drew, so you're not noticing.
Oh, okay. Let's get rid of all this crap.
Also, one thing that was kind of annoying was that, I mean, when Einstein came up with his general relativity, it was only explaining gravity. You know, they weren't expecting him to just come up with every single thing, including like exactly how protons and electrons. You know what I mean? So like, I found that to be kind of unfair, but I guess
I don't
whatever.
know. I don't think it's unfair to. I don't know what you're talking about being unfair. He came up with a preposterously vacuous explanation. It doesn't say a damn thing. It's like saying angels did it. It says nothing. It adds nothing. It's a bullshit nonsense. Time is not a dimension. It's a function of things moving from one place to another. It is not a fucking dimension.
Yeah, I agree with you on that.
Well, I don't know then why you're praising Einstein's poor dilemma. Einstein's dilemma was
Well,
he got away with complete crap, and the evidence of the crap is non-existent. Again, they haven't repeated the Eddington experiment, most famous experiment in Einstein's life, and they've never repeated this stupid thing.
well, I'm just saying that because yesterday I was talking to like a physics professor, and he basically told me that I can't like claim I have some kind of theory unless I can like explain exactly what is creating electrons and protons
Well,
and stuff.
where does Einstein do that? Oh, okay,
Exactly.
that's a
That's
huge
what I was
double
saying.
standard. Okay, well that's just a silly double standard. So yeah, he wants to cop out on a huge double standard. What physicist doesn't? They believe in their religion and they're going to try to defend it. My pope is the real pope. Your pope is a fake pope, and it's just they're just playing a game. But the point is if you want an explanation, you ask me for one, I'll give you a slight explanation. The idea could be as if there was a membrane and it trapped energy, right? So the electron has
Wait,
little
first,
bits.
so
The little
so first
bits.
the electron has a lot more blue force bits or whatever, and the proton has a lot more red force bits, right? Or is it?
Well, the idea is one is made of one thing and it constantly reflects that thing, and the other one reflects differently. So I've done that illustration a million times, but I'll do it once more just for the sake of clarity.
Sure.
There's just two very similar but opposite reactions. So the electron and the proton are two different things, and they have an inverse relationship. That is, if a red force hits an electron, or a blue force, let's say this in this case, what it does is it absorbs a piece of momentum going, okay, let's forget that one, yeah, going that way. So this piece disappears, right? The little bit there, okay, and what it does is it ends up giving back momentum in this direction, and a force will leave in this, the blue force will leave in that direction. So it ends up being this principle. Like if I hit two things together, I can have two choices of reaction. It can reflect or they could go this way, right? So when a blue thing hits a red thing, when the blue force hits so when the electron force hits a proton, it's doing this crossover thing. When the blue force hits a blue thing, it's going to just do the pure reflection thing, which means one bit leaves going this way and one bit leaves going this way.
Yeah, I understand this, and also I think that like if you did say that there's a lot of like red force bits inside the proton, let's say, then if you do enter the proton as a red force bit, you could actually go inside the proton, and then the chances are that you're going to hit a proton that's like directly facing you. That would be the tendency, right? Like you're not going to hit protons that are like moving away from you, right? So you're going to most likely hit ones that are going directly towards you, and then that's why the tendency would be that if you enter like a red matter bit and you're a red force bit, then you're going to come out where you came
Well,
in.
the argument sort of is, if you, like I said, if you understood this membrane to be flexible, the idea would be is that when the thing hits, it's really just pushing the surface in deeper. And then, yes, another piece of force from the rest of the universe has to hit it again to push it back the other way. But the idea would be is, yes, it's a container that has a certain amount of force in it, a certain number of seats, as if you thought of it as a boat. And all you're doing is exchanging a swimmer, that is a free piece of force, jumps in the boat, takes a seat, and the guy in the seat leaves. And the argument is whether the guy leaves perpendicular to the guy who jumped in, or whether he leaves in the opposite direction. So those are the two kinds of interactions. And if it's a reflection, then it's going to create repulsion between two similar objects, because the swimmer will keep going back and forth, back and forth, back and forth, back and forth, and creating pressure. And if it goes out the side, well, then there won't be any pressure. So obviously between these two bits, a red swimmer will swim into the blue object, come out perpendicularly. A blue swimmer goes into the red object, it comes out perpendicularly, so there's no reflection. You can never have anything caught between them. But if they were two red objects, then the red swimmer could get caught between them and just end up going back and forth and back and forth and back and forth.
So we have to specify that there is like something that keeps electrons and protons basically from dispersing.
I'm just saying these are so fundamental. These rules are so simple. Why do I have to do any of that? Again, nobody's there saying go dissect an electron. No, I can't dissect it. I can dissect its function. I can't dissect its internal parts. I can just speculate about it. So I'm just saying I really don't want to do speculative. I'm just saying all I have to do is meet the evidence that exists in physics. There's no experiment with which this explanation doesn't work. That's all I'm carried about. I just care about meeting the evidence and satisfactorily explaining it with simple 2 plus 2 plus 2 physics.
I guess I would have liked if I could like simplify it to not having matter bits, but I guess I can't really do that without not making sense. So yeah.
Well, I'm not saying it can't make sense. I'm just saying it's like supercomputer kind of a simulation because it's so dense and it's a pattern. All we know is there's a pattern. And you can have a durable pattern versus an indurable pattern, right? So we know there's 100 elements or 100 configuration of atom that's durable. There's lots of other configurations, but the idea is they fall apart, right? They're not durable. They can't survive the constant bombardment by the universe. But the 100 atoms, the 100 shapes can survive. And the electrons and protons are doing the same thing. They're very elemental, very from the beginning of the universe thing, and they're just durable arrangements of momentum. But we know that their momentum is completely dependent on the force that interacts with them. The force tells them where to go. The force tells them where to go. You change the force, you stick a magnet in the field that changes the forces that are hitting it, and an electron will move.
Okay, I want to talk about light also. So light is just... It has to be not. It can't just be one type of force bit, right? So there's two types of force bit in light.
No, light only affects electrons. So it's clearly just whatever color you want to make the electrons. Blue in this case, let's just say. Then north on the magnet, it's the electron force at a frequency. That's all light is. Light is just a certain amount of that blue stuff, and it's coming at a regular density at a frequency, and that's called a photon.
Okay, so it has to be blue.
It's the electron pressure. Yes, electron pressure is what photons are made out of. They move electrons.
Okay, I was thinking it might be both of them or something.
Both of them, see, it can't work because it can't get caught as if you shot the blue force at an electron, the electron moves sideways. You know, it won't convey the energy consistently in the right direction. So if you had blue force in like an electric wire, if you were pumping blue force and red force, you'd end up with yin-yang. You'd end up with mush. You wouldn't be able to push anything in any direction because everything would go sideways on you.
I guess going back to the matter stuff, like let's just say for hydrogen or whatever the first like atom is, they kind of get bonded, right? Like there's a red matter bit and a blue, and they get kind of stuck together.
Well, first you have a neutron. So yes, that's the neutron. Is when they're
Is a
stuck
neutron, is that
together.
like a mixture?
Yeah, well, when they take neutrons out of an atom, they decompose in something like 15 minutes, 12 minutes. They fall apart, and they fall apart into a proton and an electron. So
Oh, okay,
that's the
okay.
argument. So a neutron is not really neutral. A neutron is just small, and it's got a proton and an electron. It's a dipole, so
So it's like a magnet. It's like a little
yes,
magnet.
it can look neutral from a distance. It looks neutral, right? From a distance, red and blue looks like purple, right? So if you get far enough from that a red dot and a blue dot, it ends up being a purple dot, right?
Yeah.
Okay, so from a distance, a neutron looks neutral, but it's not neutral. It's the smallest dipole.
And so there's a neutron in the middle, and then there's like electrons flying around it or something.
No, there's just another a proton. So if you want to make an atom, what do? You put another proton on the other side there, and then you've got an atom, right? So if I take and put a proton right here next to this neutron, whoops, I got the wrong drawing tool. Go back to circles. If I put a proton next to it, then you can understand that all the red energy is going out the electron, all this red energy goes out the electron, and the two protons can now be incredibly close together. See, that's the strong nuclear force right there. It's not really a strong force, it's an incredibly weak force because you're pumping all of the reflective energy out. All the blue energy goes out the sides of the red things, all the red energy goes out the side of the blue thing, and therefore the two of them can get very, very close together, and so now you have a hydrogen atom in the sense that if you put an electron connected to that at one end, so you just put an electron.
Wait, could you draw all the blue? Just draw a couple of arrows, just so I can like get a better idea of like what the tendency is for the atom.
Well, I've already been over it, and you said you would. I was always drawing that, and you said you get that part. I'm just saying that look, red force hits the blue thing. Which way does it go? It goes perpendicular, right?
Yeah, I got that, but I'm just saying. So there's these things would all get squished together.
Yeah, this is the neutron, which you drew, and I just added the proton that's in the atom, right? So we know the smallest atom is a neutron and a proton and an electron.
I didn't know that.
Yeah,
Sorry.
well, that's hydrogen. One neutron, one proton, one electron. And the
Okay,
idea
where would the electron be?
would be, yeah, the electron would just sit on one end. And so now you have a polar atom. And guess what? Most hydrogen you find in the real world is molecular 2, hydrogen 2. So that means two atoms line up. So that means that the other complement to this atom just reverses. And so then you end up with a blue thing here, right? And you end up with a blue thing here, and you end up with red things in between. And that's your hydrogen 2. So hydrogen 2 would look like, well, that one ain't going to work. We just drew a new circle there. So this is hydrogen 2. And now it's a balanced atom. As you can see, it's pretty well balanced.
Yeah, so this is when they're like stuck together or something.
Well, I'm just saying that hydrogen is really small because, yeah, the electrons are close because the whole thing is stuck together, right? So, but I'm just saying you have the essence of the object. You have one neutron, one proton, one electron. You have two molecules that stick to each other because the hydrogen 1 is very polar, and therefore it doesn't exist in the real world, in the environment, because it is so reactive in the sense that it's so polarized, right? I mean, it has this blue thing at one end and a red thing at the other end. It's completely polarized. But if two of them stick together, then they become dipoles all the way around. All the way around, it's red, blue, red, blue, red, red, blue.
Okay. I guess maybe we could talk more about magnetism, because there's two things I'm confused about. Well, it's mostly like the electron, how the electron proton like formation would lead to a little mini magnet, and then also how would stacking them on top of each other increase their magnetic effect.
It's the same argument. So if you really have to understand the left turn argument or the right turn argument. So if you understand that the two forces act completely opposite to each other, then you can understand that it's pretty simple. So if I have a magnet, and we'll just say this is an atom, All right, we can just say you understand it's an electron and a proton close to each other.
Sure.
Right. Or it's a lot of electrons, 5 electrons on one side, and two protons on the other side, whatever you want to say. But I'm just saying it's polarized. And the idea is the same idea. So if the red force, yeah, you don't really need that part, but okay. It's just so if you just understand, it's just a right hand rule. So I'm just saying, if you understand that if a blue force goes into this red thing, what they're going to do goes this way.
Either way, right?
Not either way. No, it goes this way. Right hand rule. Turns right. All right, if it goes into the top red you drew up there, it goes to the same thing, goes into the blue, but it all passes right through. So it passes through this border. So if you understand, this border doesn't really exist. So once they get close enough, just passes through that border and becomes part of what this end is producing. Now, if you understand that every bit of blue energy that goes in comes back out as a reflection. So all the blues are doing this, right? All the blues are radiating back out to the world. And any red that goes into this magnet doesn't radiate back out. It goes straight through, comes out the red side eventually. And so it's that simple. It's like all the red energy is getting absorbed by the blue side and coming out the red end. All the blue energy is, it's the same thing happening. All the red stuff's reflecting off red, all the blue is reflecting off blue, and the red ends up going into the red and coming out the red side, and the blue ends up going through the blue and out the blue side. And that's it.
I guess well, now that you're using the right hand rule, it's kind of I don't think I was thinking of it that way. So
well, strictly speaking, it's not a right-hand rule, okay? It's just a turn. But I'm just saying the turn would be towards the magnet. So you can understand that if that red comes in from the left side, or if it comes in from the right side, right, left, and right are going to be two different directions. The idea is that obviously turns towards the proton is the argument. So if this was the electron, the energy turns towards the proton side when the two are next to each other. So it just keeps going straight through until it gets to the surface of the red end where it comes out. So all the red energy that hits blues is all getting pumped to the red end. All the blue energy that hits reds is getting pumped to the blue end, and the rest are just reflections.
Oh wow, I think that makes sense actually. Yeah, I think that's pretty good.
Okay.
And it's not gonna like, if the magnet is too big, it's not gonna like cause like a double collision or something like that.
Well, there's no too big a magnet, right? Because we know the magnet's made out of atoms, so we know it's like Legos. There's no such thing as too big a Lego, right? I mean, the more atoms you line up, the more filtering you're creating. It's a filter, right? All we're saying is it filters. When purple comes in, the blue stuff reflects out of one end, and the red stuff reflects out of the other end. That's the rule, right? So an idea of purple coming in and blue and red being separated. And each one of those little atoms is going to do that. Each little atom is going to say, if it comes to me purple, it's going to come out of me red and blue.
Okay, I think I got that. What else is there?
Well, you don't have to force it. we can do this every couple of days or whenever you want. So when you have more questions, you can ask.
Yeah, it's kind of annoying that, like if I talk to teachers, it's like they're usually busy, or like they're not on the payroll or something. So it's like I'm kind of.
Yeah, no, I mean, the only way to do this is to actually pay somebody to take the time, because it takes a little bit of time, right? I mean, you have to take at least a half hour to get the theme. And, if they're not going to put in the time, they're not going to get any of it. So, it's clearly a huge obstacle. But I mean, on certain subjects, I think you can nail them on things where they've got it wrong, like polarized light. The 3-filter light example, it just makes it so obvious the light isn't being destructively broken.
Well, for me, gravity is a pretty easy one. They usually go to like gravitational waves, which came out like 6 years ago and had Einstein didn't even have a clue what those were, and he didn't even.
Well, he did. He
And
did have an opinion. They just didn't care to listen to Einstein. Einstein said it was such a minor effect that you'd never be able to detect it more than 10 feet away from the object. So it's so weak a difference. I mean, all Einstein was saying was that, when you have gravity waves, what you're going to do is circle. It's kind of a simple argument. You'll have two objects in space that are orbiting each other, right? And there's two kinds of positions. So say if you're an eyeball looking at it from over here, right? You're looking up at these two objects. There's two fundamental positions they'll have. That is when they're left and right of each other, and when they're forward and back of each other. And the truth is, the center of gravity for those two positions is slightly different. So the center of gravity, right, when you have the two objects lined up, is a little bit closer, is here, where the center of gravity when they're right and left is here. And that's really the wave. The wave is just the fact that you're changing the center of gravity of this four object. You know what I'm saying? It's two objects, but you're changing the center of gravity of those two objects when they circle. Because there's a little more gravity when they're lined up, and a little less gravity when they're side to side. And you can sort of understand that as the dispersion argument in charge, right? As charge is dispersed, the same would be true of two charges. If you put two negative charges in line, the charge will be slightly stronger than if the two charges are parallel to each other sideways, tangential, however you want to just perpendicular. Because they're more dispersed, right? You can sort of see that the charge is concentrated when they're up and down, and the charge is dispersed over more space when the two charges are further apart from each other horizontally. And it's the same. So that's what Einstein thought of as a gravitational wave. He didn't think you could convert matter into a wave. He just knew the subtle change in this position of the center of gravity would create a slight increase and decrease in the gravitational field as the two objects spun around a common center. So when you have what do you call that? A dipolar sun? What do you call them when the two suns are orbiting each other? There's a word for that.
I think it's by something.
Well, anyway, I just can't remember the word. Well, anyway, but the point is, when you have that circumstance, there's a tiny change in the intensity of the field, and that tiny change is theoretically creating a gravity wave. It's a
it's called binary.
Binary star.
Binary,
Right. So when you have a binary system, two things, they have a center of gravity they're orbiting around. Okay, there's nothing in it, but there's a center of gravity, and that center of gravity literally does change depending on the position of the two objects. But it's a tiny, tiny change, and Einstein said, no chance you're going to see that for more than 10 miles away. Okay, you're 10 miles away, you're done feeling any difference, being able to detect any difference. It's so tiny. And the LIGO people have decided a whole new kind of math. They decide they can convert actual mass into gravity. They can convert mass into bent space, and so they say 3 solar masses were lost into this energy, and therefore they're making a justification for where all the energy comes from for us to be able to see the damn thing. But we can't see it by the Einstein's description of a gravity wave has nothing to do with their description of a gravity wave. It's completely different physics.
Yeah, I can already tell that they're kind of thinking of something wobbling in space or something, and it's already clearly they haven't measured anything like that, or they haven't shown that to be what's happening. But,
well, like I said, the wobble would be a real thing. They don't have a wobble. The problem is the only way they can make this thing possible is they have to convert matter into energy to make it visible. And that's the key thing they did. And they did it without any scrutiny. Kip Thorne just decided, I'm going to make up a physical principle. And nobody critiqued it. Nobody said that's crazy. They all just said, fine, okay, you can convert matter into bent space. Fine.
Yeah. Okay, so so I guess I wanted to ask you one thing, but it's not really criticizing you as much as it's just trying to criticize them when they say something like they'll basically say that there's a star that they can look at, and then there's a star behind it, and the light somehow bends around the star, and they're claiming that we can end up seeing it here on Earth.
Yeah, I know they claim it. So what? There's absolutely no evidence of any such thing. So they don't have any
Yeah,
evidence.
and they usually show one picture as evidence. Like they'll show you one picture and they'll tell you this happening, right? But shouldn't they have
Well,
like
but
two
we
different
can go back
pictures?
to Einstein again. Einstein rings, by Einstein's own words, impossible to see. Because an Einstein ring would be so thin, right? The ring would be so thin, it would be impossible for us to see it. That's Einstein, right? And so they still call it Einstein rings, and yet they claim they have pictures of them. They're obviously not Einstein rings because they're big, fat, thick things that are completely non-symmetrical, and large gravity becomes very symmetrical. So there's no way you could get around having perfect symmetry. And these images have no symmetry. They're huge, hundreds of light years of space across. They're gigantic. An Einstein ring should be like 6 photons across. They have Einstein rings that are hundreds of light years across. It makes no mathematical sense. It's just rubbish. And again, the point is we have thousands of satellites in space. If they could do this see things behind star thing, they could do it every day from space, and they don't even try.
So like I was just thinking that if they did have this idea, because like I saw this animation where they were saying that they were claiming that this happens, right? And they showed it as an animation, and they basically showed it like, let's just say, do you see this group of dots that I drew?
I know, but they show black holes and they show animations that they made in a blender. I'm just saying, just because they say something is true doesn't mean there's any evidence whatsoever for it. I'm saying there's absolutely no physical evidence of us ever seeing a star behind another star. They have no photograph anywhere of such an event.
Yeah, but the thing is that if they did want to show me like something to convince me, right, they'd have to show me two pictures, like one of them before the eclipse or before the stars in the way,
Well,
and
I
one
know, but
after,
you don't
right?
need an eclipse. That's the whole point. From space, you don't need it. The only reason why they needed an eclipse on Earth is because of atmosphere making it impossible to see space during the day. So you
Yeah,
can't see behind the sun because the sun's not out. So, but from space you can do it every single day. Every single day you could look right near the corona of the sun, and you could see stars pop in and out, and you could watch them move in funny directions. Because theoretically the consequence of lensing would be is you would see the star where it wasn't, but then when it was in certain locations it would disappear. So because of the lensing. So the fact is the star behind the sun should actually move out, move backwards, disappear, and then jump to its original position. So, and none of that. They don't have a single video of any of that ever happening, because it doesn't happen, because it's a story, because it's not the truth, because it's no evidence for it. Light is not bent by gravity. There's no evidence supporting the theory.
yeah, I agree with you that there's no evidence, but the thing is that when they show evidence, like they'll say it's from Earth, so they're claiming that they can only see it from Earth. So let's just say that you have to be on Earth or something, and
No,
that's the only way to
well, I'm
find
just
it.
saying, I want to argue nonsense. It's obviously stupid. I mean, it's only a couple of thousand miles you have to go to get to space, okay? It's only 2,000 miles and you're in space. So obviously, that's a bogus, silly, nonsensical mush. You can see so much better from space. That's why they put the Hubble telescope in space, is because you see so much better.
Yeah, but I guess I'll argue a bit of nonsense. Like basically what would happen is you'd actually notice between T1 and T2, like you would see it would look very different basically when the star was in the way and when the star wasn't in the way. And if they wanted to show me some kind of evidence, like they'd have to show me before and after, and then they'd have to show me
I'm
that
just saying they could
things look
video
very
it. They
different.
could do it right now. They could videotape it from space. It's really easy to do. They don't do it. That's the point. So I don't know what to tell
Yeah.
you. The whole theory is nonsense. And if they could produce the evidence relatively easily, and they've never tried because they know they're going to fail. And failure means they have to throw out the whole frickin' Einstein bullshit.
Yep. Okay. What about electricity, real quick? I think I got it, but maybe I could. I guess you have to undo.
Well, there's
So
several.
electricity is not too bad, right? It's just the electrons are going through the wire. You said they're not moving through it,
No,
through the
it's
wire?
just pressure moving through the wire. So we're back to, you have to, electricity is completely an atomic phenomenon. It has nothing to do with anything else. There's no such thing as electricity. Electricity is an event that takes place between atoms. So that's the first thing you got to understand. There's no such thing as electricity. there's photons, that is energy, but there's no electricity. And electricity is just a consequence of the fact that when atoms are connected to each other, that is, they're in space, they automatically regularize to the forces they're in. So they're jiggling each other, and they all sit in a peaceful place, right? An arrangement that's peaceful for them. That is where the tensions are all even. And what electricity is basically you're just saying, I'm going to hit this electron with a force. Back to arrows again. So I'm going to hit this little electron with a force. When I do that, it's going to move the electron. When the electron moves, it's going to create more back and forth force between that electron and this electron. The force is going to increase the pressure, which means this electron will move. And then that'll mean that the other electron will move, and the next electron will move. And they'll push each other. Now, with alternating current, it doesn't become a problem because, you can just keep moving the same electrons back and forth, and you're really not doing much. But DC current will require you to actually, eventually, I would theorize, you're actually piling up electrons at the other, you end up moving the electrons. They move much slower than the speed of light, but they move through the wire, but you keep pushing this one, you keep pushing it, you keep pushing it, you keep pushing it, you keep pushing it.
I mean, if you have a capacitor at the end, right, then it's just it might store some of those electrons at the end, right?
Yeah, well, the key thing is the pressure. You can increase the pressure almost exponentially. That is, the voltage between electrons can become huge. So if I put two electrons really close to each other, you can understand that I can create intense amounts of pressure if you understand the ping pong paddle kind of argument, right? So you have two objects with a force moving back and forth between them, right? So you have all this force going back and forth here. And as I move them closer together, that force is going to get more and more intense, right? So there's more and more interactions, right? You can get that, right?
Yeah.
As that distance shortens, there's more and more hits, more and more hits, more and more hits. So as I bring those closer together, you can see that can almost become infinite, right? I mean, I can make the space between those two objects so small that there's 1 trillion hits per second, right? Where at the further distance, there's 1 hit per second. I can make it 1 trillion hits per second. So I can create incredible pressure between the electrons. And so those trillion hits means real pressure. That means it's a real kind of ability to move. So you can move those electrons incredibly fast away from each other if they're moving into low pressure. So that the speed of that electron can get up to the speed of light instantaneously almost, because it has so much built up pressure. So the closer I can move the electrons, the faster I can move them. So the closer I put them together, the faster they can move away. And that's all real momentum.
So what's happening in the capacitor is you're saying it's not storing electrons like on top of each other or anything like that?
No, it's just pushing electrons. It's storing electrons in that you're adding electrons. But the real pressure is in the pressure between the electrons building up. So the pressure is the fact that when I make those electrons a little bit closer together, I'm increasing the number of impacts. And that's happening to every single electron. As I shove a couple more electrons in, each electron represents trillions of impacts. You know what I mean?
Yeah.
So you have to think of the electron as space. You're closing the space. You're eliminating the free space. So you're pushing all the ping pong paddles closer and closer together, and each set of paddles has a little ball bouncing between it that's hitting more and more times, and each impact is energy. So you're really just counting. When you're counting the energy in the system, you're counting the interactions in the system. You're not counting the number of bits in the system. You're counting the number of times the bit hits something. Interactions are energy.
Yeah, and if there's movement basically of electrons that leads to the magnetic field, it's basically just like a filtering effect.
Well, I'm just saying,
because...
yes. The point is if you compress something that has ping pong balls in it, the ping pong balls are going to have more and more interactions, right? So if I have a ping pong ball in a balloon and it constantly just bounces back and forth, the smaller I make the balloon, the more times the ping pong ball hits the surface of the balloon. Yeah. So it has more energy. The smaller I make it, the more energy I give it. That's the key to understanding. So when I'm filling up a capacitor, filling up a battery, all I'm doing is I'm pushing the electrons into each other, compressing the force, which is creating more capacity for the electrons to move away.
Okay. I guess that was good.
Okay.
Wait, did you say in a video that you were gonna like stop smoking and wear a suit or something like that?
I said that might be a reasonable thing to do someday, but I don't think it's actually going to happen. I was sort of being sarcastic and satirical because
Okay.
I obviously shouldn't have to do those things, but I might clean up.
Yeah, I don't think you should have to do that.
Oh, I'll clean up my act a little, maybe, but we'll see how much I have to clean it up. I mean, I'm working on my language. I mean,
Yeah, whatever.
you have to make yourself less repulsive to the world. Apparently, that's important to people.
Yeah, and it kind of sucks to do that. But I guess I'll just go back to this to kind of the first thing I was asking you about, just to like maybe we can get a little bit more insight on it.
Uh, I don't know. I don't remember what the first thing was. What are you saying?
It was just with the three objects. Like essentially, you'd have 100% of the force field here, right? So you'd have 100%.
I'm going to argue to you, you can't destroy the momentum in a direction. So there's no way to have 100% here and then say, well, over here, there's only 90% of the energy. The energy is just moving slower. So it's still affecting this at the speed of light. These two things are communicating with each other. So any change you make to this object, you're going to make it to this object. So you never can undo the momentum. So if the momentum is coming in this direction, right, you can't undo it because parts of this are now going to move this way. And when those parts move that way, you created a new surface here that's closer to this object. Now this object is going to know this thing has moved closer to it. To move closer to it, it absorb force, which means this object is going to move closer to this object, right? But, okay, the key is that you have this third object that's also in play, which is pulling on both of them, and neither one of them can move towards each other while this object is pulling them both this way. But I'm just saying you can't undo the force. I'm just saying, look, think of it as the force hitting the Earth. What happens to the surface of the Earth? It increases the pressure as you go down, right? So when I go inside the Earth, what happens? The pressure gets intense. I go down 100 feet down, I can burst your eardrums, right? If I put you 100 feet of water, I'll burst your eardrums. I put you in 1,000 feet of water, I'll smush your whole flesh will get smushed in, and all the gases will come bubbling out of you. All right, there's tremendous pressure. So it wasn't like the momentum disappeared. The momentum, it is converted into the movement of matter. So you can't consume the momentum. You are only changing what form the momentum is in. You're converting it from a speed of light force into big heavy balls rolling. But the big heavy balls are still rolling towards the other object. So the momentum is still there because it's moving closer to the other object. So it's going to be imposing its momentum is still going to be getting to that other object. It's just going to get there through a couple of translations from force back into matter and then back into force and then back into matter. But the momentum is always there. You can't kill the momentum. If you kick something with your foot, you know the energy isn't destroyed. The motion of your foot went into whatever the hell you kicked, and it's still there. You can always follow the energy. And it's still there. It never dies. It just gets transferred to different objects.
I'll probably think about it and then maybe be able to...
Well, just think of the fact that it turns it into chemical pressure.
Yeah, I understand that it's turning it into matter, kind of the movement of matter, right?
I'm just saying, yes. So whatever you're just saying that there's a bunch of stuff coming at you, bullets, and let's say there was a field in front of me of apples, and now the bullets hit the apples, and I'm going to say, well, now some of the force has been consumed. Well, I know none of the force was consumed, right? I know the bits of the apples are going to head for me, right? So I didn't really consume any of the momentum. I'm just slowing down the bullets. And now bigger pieces are like, let's use something different. Let's use, hard steel balls. So the bullets hit the hard steel balls, now I got big steel balls heading for me. So it's not like in any way I've diluted the force. The force is now just in a different form that's moving a different speed, but it's still heading right for me.
Okay, I think that's pretty much it. Maybe we could talk about light a little bit, but it's already been an hour about, so
Yeah,
maybe
that's
not.
okay with me. We can do it next time if you got some more stuff and such.
I'll just do real quick. So for light between I'm just curious, like when it hits an electron, when it hits an atom, because light comes from the sun and then it hits all these atoms, and then different atoms have different properties that make the light come out at a different frequency, right?
I think the easier way to understand it is to understand that it's another one of these transfer things. You're changing something, moving into the speed of light to changing it into the momentum of electrons. And so what you really have to think about it as is if you thought of everything as just being a surface, and all you're really going to do is change the surface. So you're going to basically dent the surface over here by hitting it, right? You hit it with something, you dent the surface here, and you're going to pop the surface out over here, right? And each time you pop the surface out, what does that mean for all those little arrows that were coming in, right? All these little arrows were coming in, and they were going to hit this surface back here. Now they're going to hit this surface much closer. So these arrows are going to come back feeling like more energy because they came back sooner, right? In a specific amount of time, they moved from point A over here to some other point in less time because you push this surface out, right? And then the surface moves back in, and the surface moves back out. The photon hits at regular intervals, so it pushes here, pushes this surface out. Now the surface reflects differently to the world, all right? And that's, you're just translating what happened on one side to the other side of the surface. So you just moved electrons this way in here, and you move them out on the other side. And now the reflection is just a different reflection. Just if I move closer to the camera, it's reflecting a different image than when I'm further away from the camera.
So is it like an 100% collision? Like if you do enter into the electron, like as long as you actually enter inside the electron, you'll actually have a collision in there?
Yeah, well, the momentum is conserved. So yes, it's just hard things hitting hard things. Momentum is just absorbed, and the big thing moves at a slower speed, and then its force between the two electrons increases. That means the one electron has to stop moving because there's more force now, and the other electron starts moving because it got hit by more force in the opposite direction. So the force just keeps migrating between the pressure between the electrons. So the electrons have pressure between them. The pressure just moves from one electron, pushes on the next electron, causes it to move. The next electron moves. The next electron moves. They all just push each other, and eventually you push out the surface, and then that surface pushes back in, and that's when it gives back the energy that's the photon.
All right. I guess one last question. You said you have to be moving at the speed of sound to produce light, but can you just like
No, you have to move
switch like a
faster.
sword?
No, you have to move faster than the speed of sound to produce sound.
But can you just like swish a sword or something in the air and it makes it
No,
won't be faster than the speed of sound?
it's only going to make a sound if it moves atoms. So when you swish a sword in the air, what you're doing is some of the atoms you're hitting straight on, some of them you're pushing faster, some of them you're doing a lot of different things to. Some of them will actually be moving faster than the sword you're swishing through the air is the point. And those are the ones that are going to make the sound. So you have to move an atom faster than the speed of sound for it to communicate sound, for it to bang into another atom at the right speed to communicate the pressure. So it's atom to atom pressure, and the point is that you have to have some motion that's faster than the speed of sound to initiate the chain reaction that'll cause one atom to bang into another atom, to bang into another atom, to bang into another atom. Any less than that energy, and it won't go anywhere. It's like
Okay.
Newton's cradle, or some other thing. I don't, there's a minimum amount of energy you need to have a sustainable chain reaction, and that's sort of what you're depending on, is a kind of chain reaction, a kind of thing where it forces one atom to just move into one atom. Instead of moving to a bunch of atoms, it just moves into one. And all the energy is transferred from one atom to the next atom to the next atom, and then you'll have a durable wave of sound.
All right. I think that should be good.
Okay. So, till the next time and such then.
All right.
And
I'll
so
see
forth
you.
and whatnot. Okay. Happy
Thanks for
trails.
thanks for the lesson.
Good luck arguing with the world and such.
Yep. All right. See you.
Right. Skype. There it is. Skype. And close that. don't think there's anything too interesting you saw. Don't think so. All right. Anyway, that should be enough. So anyway, sorry I get cranky, but it really is irritating. Yeah. Even when it's friendly fire, it's still, oh, you have to say this again. Oh, I have to go over this again. But it's part of my job now, unfortunately. Okay, so till next time and such.